Hello, our last objective in this unit is to estimate area using trapezoids. Trapezoids have a slightly more complicated formula. The formula for a trapezoid is area is equal to 1/2 times base 1 plus base 2 times the height. And just so you're all aware, every time we do this in calculus, our trapezoids typically tend to look like this, and our bases are typically not what you would think of the bases. They're the sides, and our height is the distance between them. So it's kind of like a sideways trapezoid. It's going to be like that every single time. And what you really need to know is that the height is the change in x, so that's delta x or dx. And then the base 1 and base 2 are going to be like the two y values on any given trapezoid. So our first problem asks us to estimate the area from 3 to 9 using two trapezoids of equal width. So from 3 to 9 is a distance of 6. And since they're asking us to use two trapezoids, we're going to divide that by 2. So each trapezoid is going to be a width of 3. This isn't really a surprise if you look at this picture because it seems to count by 3s anyway. So our first trapezoid goes from 3 to 6, distance of 3. And our second trapezoid goes from 6 to 9, distance of 3. So we're not finding this whole area. We're just going from 3 to 9. And trapezoids, unlike rectangles, use both the left and the right side. So I'm going to draw a line for this left trapezoid and basically just connect these is what this looks like. That's supposed to be a straight line. You can see the trapezoid there. And it's pretty good as an estimator compared to rectangles that always had that extra little piece hanging off. Same thing on the right side. If you connect it right there, and then connect the left side and the right side, you end up with a trapezoid that is much better as an estimator compared to rectangles. So now we're just gonna go for the formula. So our height at that first one is 1. The height here is 3. The height there is also 1. So you can probably tell if these trapezoids have the same height, so I really could just find one and double it. That's fine, do that if you want, but I'm going to show all the work for this because it won't always be like that. So our area is going to be, the first trapezoid is 1/2, and then base 1 plus base 2 are the two y values, so that's 1 plus 3. And then times the height, or the change in x, the distance from 3 to 6 is 3, which we had determined earlier. So that's our first trapezoid. Our second trapezoid also has a 1/2. This time our two y values are 3 and 1, so these two trapezoids share that side in the middle. And then it also has a dx of 3. When you do this, you can always factor stuff out, like the 1/2 or the 3, or basically anything. Kind of do whatever you want when it comes to this. If it makes it easier for you, as long as you get the same answer in the end, will be good. When you calculate all this, it comes out to an area of 12. So the area of those two trapezoids together is pretty close to that curved area, and that estimation comes out to be 12. The next problem does not give us a picture, but it does give us all the y values and all the x values, and it says estimate the area using trapezoids and the given subintervals. So we don't need to determine anything here at all. But what you notice is the dx from each one of these x's to the next x always seems to be the same. It seems like they're clearly counting by 0.5s. I'm not going to write that for each one. But that will make it easy. So our dx is always going to be 0.5. And then our first trapezoid goes from from negative 1.5 to negative 1, and the two y values are negative 1 and negative 4. The next one goes from negative 4 to negative 6. I keep saying the y values, but the point I'm trying to make is that these trapezoids share a side together. And then it keeps on going like that. So I'm gonna get started here like this. Because the formula for a trapezoid always has a 1/2 out front, And because the dx in this case is the same, I'm going to try to make my life a little bit easier by factoring out a 1/2 and the dx of 0.5, which is also 1/2. You do not need to do this, but it's going to save me writing that a bunch of times. So that being the case, my first trapezoid, the only thing I need to worry about then is the y1 plus y2, or the base 1 plus base 2. So that's from that's -1 and -4. So -1 plus -4. The next one, the y values are -4 and -6. So -4 and -6. Again, you notice I left the 1/2 and the 0.5 out. And all the rest I'll just do in black. The next one goes from -6 and has -7 as the other y value. The next one, -7 back to -6. The next one, -6 and -4. And then the last one, -4 and -1. Sorry, -4 plus -1. You notice that if I had not factored out the 1/2 and the 0.5, I would have had to write that for every single set of parentheses here, which isn't the worst thing in the world, but I just didn't feel like doing it. So what I'm going to do now is type all this into the calculator and get an answer. When I type all this in, it comes out to -14. So our trapezoid approximation is -14. Again, any shortcuts you want to make, like factoring stuff out, is good. What I want you to notice also, in rectangles, when we do rectangles, either the leftmost or the rightmost y value is always left off, but that's not the case here. Trapezoids use every piece of information that you need. The third example gives you a function but does not give you the y values. That's fine. This is a little bit more, but we'll just have to make the table ourselves. You notice that they asked for the integral from 0 to 1, so that's a distance of 1. And they asked for 4 trapezoids. So if we take that distance and divide it by 4, we get 0.25. You don't need to show this. You can probably do this in your head a lot anyway. But what that means is we are going to need to make this ourselves. So it starts at 0. It's counting by 0.25s. And if we do this right, if we do this right, it should end at 1. So 0.25, 0.5, 0.75, and then 1. For the y values, just like in the last video, we need to find f of 0. We need to find f of 0.25. I'm going to round everything to 3 decimal places. This is really just calculator work. When I do that, I'm gonna skip ahead. Hopefully you guys all know what I'm doing. I'm just plugging in these x values into the function. I'm getting 0, 0. 0.25 has a y value of 0.016. 0.5 has 0.125. 0.75 has 0.423. And then 1 has a y value of 1. So once I have all this information, now I'm good to go with my trapezoids. I'm going to erase this. I did it all in the calculator. All right. So our dx in each one of these cases is 0.25. I'm not going to show it every time, but it is. And then here's all our y values on the bottom row. So when we do this, our first trapezoid is 1/2 times base 1 plus base 2 is 0 plus 0.016 times the dx, which is 0.25. You notice this time I'm just doing it the long way. I didn't factor anything out. I just wanted to show you what that looks like too. The next one, the next trapezoid goes from 0.016 to 0.125 with the same dx of 0.25. The next one is 1/2 and then 0.125 to 0.423 with the same dx of 0.25. And then the last one, the last trapezoid is 1/2 and then 0.423 plus 1 with a dx of 0.25. I'm going to type all this into the calculator to get my final answer. And let's see. This comes out to approximately 0.266. And that's it. The last thing we need to talk about is how to tell if your estimation is too high or too low. We're going to do this using the exact same, just kind of draw a picture and see strategy that we used in the last video. So what I would like you guys to do is this. Can you draw two functions that are both concave up? So I'm going to draw increasing concave up, and I'm going to draw decreasing concave up. And what I want you to notice is that when you draw a trapezoid here, like that, you should be able to tell if a concave up function is too high or too low of an estimation. It should be easy to tell. We've got a little bit of extra right there and a little bit of extra right there. And the reason I had you do two is this. And when it comes to rectangles, your estimation being too high or too low is based on if the graph is increasing or decreasing. But here I wanted you to see that it was not based on that. It's based on concavity. So what I would like you to write down is this. If the function is concave up, then trapezoids overestimate. We're going to do the exact same thing going the other way and come to the opposite conclusion. So I'm going to draw a graph that is increasing but concave down, and another graph this time that's decreasing but concave down. And when you draw trapezoids in here, you're going to see that these trapezoids are all slight underestimates. In this case, it misses that little area. In this case, it misses this little area. So our final conclusion here is if a function is concave down, then trapezoids estimate the area. And that is it.